After the discussion of the terminology for the wave, we discuss frequency, angular frequency, periodic time, right? And also the wavelength and wave number for a wave. Now there are two quantities still remaining, that is the wave vector and what is the wave velocity. So sometimes the 2 marks question is also asked like that way. Define or they explain wave vector and wave velocity. Right? Now, what is the wave vector? Wave vector is that the decrease in phase in unit distance along the direction of propagation of the wave is known as the wave vector. Again, the decrease in phase in unit distance along the direction of propagation of a wave, that is known as the wave vector. Now friends, already we know that is the wave propagating along the positive x direction. Already we define the wavelength. Wavelength is the distance between the two particles having the phase difference is of 2 pi radian. Here we consider these two particles having the phase difference is 2 pi radian. So that is known as the lambda or the wavelength of a wave. Again, the distance between the two particles having the phase difference of 2 pi radian is known as the wavelength. It means as we are going from this particle to this particle, the phase is decreased by 2 pi radian. Right? Therefore, whatever the decrease in phase in unit distance, that is known as wave vector. Again, we repeat the definition. The decrease in phase in unit distance along the direction of propagation of a wave is called the wave vector, and that is denoted by symbol K. Along the direction of propagation of a wave. In distance lambda, decrease in phase is 2 pi radian. Therefore, in unit distance, the decrease in phase is 2 pi upon lambda. Therefore, that is the K is equal to 2 pi upon lambda. So, K is the wave vector, or that is also known as the angular wave number. Because we know that wave number V bar is equal to 1 upon lambda. Yes, we multiply by 2 pi. So, that becomes the wave vector. And that is also known as the propagation constant. SI unit of K is radian per meter. Now again we repeat, what is the wave vector? The decrease in phase in unit distance along the direction of propagation of the wave. That is known as wave vector. Again we repeat, the decrease in phase in unit distance. In which direction? Along the direction of propagation of a wave is known as the wave vector. It is denoted by K. Already we know that along the direction of propagation of a wave, in lambda distance, the decrease in phase is 2 pi radian. Therefore, in unit distance, the decrease in phase is 2 pi upon lambda. That is our wave vector. And that is K is equal to 2 pi upon lambda. Now we know that wave number V bar is equal to 1 upon lambda. Right? Okay. Therefore, as we multiply both sides by 2 pi, so that becomes the wave vector. Therefore, wave vector K is equal to 2 pi upon lambda. And it is also known as the wave vector or the angular wave number or the propagation constant. Its SI unit is radian per meter. Because the SI unit of wavelength is meter, therefore 2 pi upon lambda, that means the radian per meter. That is the SI unit of wave vector. Now, what is the wave velocity? V. The distance traveled by the disturbance along the direction of propagation of a wave in unit time is known as the wave velocity. Already we know that what is the velocity? The distance traveled in unit time, that is known as the velocity. Here the wave velocity, that means the distance traveled by the disturbance along the direction of propagation of a wave is known as the wave velocity. It is denoted by the symbol of velocity v. Now we know that the distance between, or the wavelength, is equal to this distance. That means the distance between the two particles having the phase difference is 2 pi radian. And the time taken to travel this distance of lambda is known as the periodic time. Is known as the periodic time. Okay. Therefore, the distance traveled by the disturbance in time t is lambda. Is lambda. Because there is the one oscillation is completed. Our definition of the periodic time t is the time taken to complete the one oscillation is the periodic time. In periodic time t, the disturbance traveled, the distance is equal to lambda. Is equal to lambda. Therefore, the distance traveled by disturbance in unit time is just mean the distance traveled by disturbance in time t is lambda. Therefore, the distance traveled by disturbance in unit time is lambda upon t. Lambda upon t. Therefore, the wave velocity is equal to lambda upon t. But we know that f is equal to 1 upon t. Therefore, v is equal to f lambda. V is equal to f lambda. As we multiply and divided the right hand side of this equation by 2 pi radian, so we obtain v is equal to 2 pi f into lambda upon 2 pi. Multiply by 2 pi and divided by 2 pi radian. So 2 pi f, we know that omega, and we know that the wave vector k is equal to 2 pi upon lambda. Here, reciprocal of this, lambda upon 2 pi, therefore k is in denominator. Therefore, wave velocity is equal to ratio of angular frequency to the wave vector. V is equal to omega upon k. Again we repeat, what is the wave velocity? The distance traveled by distance along the direction of propagation of a wave in unit time is known as the wave velocity. It is denoted by v. Now we know that distance traveled by disturbance in time t is lambda. Therefore, the distance traveled by disturbance in unit time is lambda upon t. And that is our wave velocity. V is equal to lambda upon capital T. But we know that 1 upon t is f. Therefore, f into lambda. Now, right hand side is divided and multiplied by 2 pi radian. Therefore, v is equal to 2 pi f into lambda upon 2 pi. 2 pi f omega. And k is equal to 2 pi upon lambda. But here lambda upon 2 pi. Therefore, 1 upon k. Therefore, v is equal to omega upon k. And therefore, v is equal to ratio of angular frequency to the wave vector. Clear this? So, there is about the wave vector and also the wave velocity. The definition of wave vector, the decrease in phase in unit distance along the direction of propagation of a wave is known as the wave vector. While the wave velocity is the distance traveled by a disturbance in unit time along the direction of propagation of the wave. Clear this? Okay. After that, the next question is that write wave equation for one-dimensional progressive harmonic wave traveling or the propagating along positive x direction and explain. Again, write wave equation for one-dimensional progressive harmonic wave propagating along positive x direction and explain it. Therefore, the wave equation for one-dimensional progressive harmonic wave propagating along positive x direction is denoted by y is equal to a sine omega t minus kx plus phi. Now we know that y is the displacement of the particle taking the part in the propagation of a wave. A is the amplitude of a wave, omega is the angular frequency, k is the wave vector, and phi is initial phase or the phase constant or the epoch. Again, the wave equation for one-dimensional progressive harmonic wave propagating along positive x direction is y is equal to a sine omega t minus kx plus phi, where the phi is known as the initial phase or the phase constant or the epoch. Y is the displacement of oscillating particle taking the part in the propagation of a wave. A is the amplitude of a wave, omega is the angular frequency, k is the wave vector. Right? Okay. Now, phi is the phase of a particle at x is equal to 0 and at time t is equal to 0. That means there is the phase at initial phase at time t is equal to 0. This above equation y is equal to a sine omega t minus kx plus phi represents the displacement of a particle at distance x from the origin of a wave or the source of a wave at time t. Actually, this equation y is equal to a sine omega t minus kx plus phi represents the displacement of a particle at distance x from the origin of a wave and also at time t. Clear? Okay. Now we also discuss about the other term. Now, already the equation of one-dimensional progressive harmonic wave propagating along the positive x direction is y is equal to a sine omega t minus kx plus phi. Just we discuss about the initial phase or what is the phase of the wave. Right? Okay. Now, here the phi is represent the initial phase of a wave. Initial phase, that means what is the initial position of a particle which performing the simple harmonic motion at x is equal to 0 and at time t is equal to 0. Now, the wave equation y is equal to a sine omega t minus kx plus phi. In above equation, the angle with the sine function is omega t minus kx plus phi. Gives the total phase of a particle at a distance x from the origin or the source of a wave and at time t. Now listen, already we discussed about the phi. Phi is the initial phase. That means the initial phase of a particle oscillating or the performing simple harmonic motion at x is equal to 0 and at time t is equal to 0. While this equation, the angle with the sine function, this angle is omega t minus kx plus phi, gives the total phase of a particle at distance x from the source of a wave and at time t, at any time t. It is denoted by theta. Therefore, theta is equal to omega t minus kx plus phi. Initial phase plus this term. Addition of the initial phase and this term gives the total phase of a particle at distance x and at any time t. The rate of change of theta with respect to distance x at time t is d theta upon dx. We take the derivative of this equation with respect to x. Therefore, d by dx of omega t minus kx plus phi. Omega is constant, t is also constant with respect to x, and phi is also constant, that is the initial phase. Only the derivative of this term is minus k. Minus k. How we take the derivative? Like this way. Therefore, d by dx of minus kx. Minus k is constant, taken out. Dx by dx. So this dx by dx is equal to 1. Therefore, minus k. Omega t and phi are the constant. Derivative of constant is 0. There is no change in omega t with respect to x, and there is no change in initial phi with respect to x. Therefore, both are constant, derivative are 0. Only we have to take the derivative of this middle term, minus kx. Derivative of minus kx with respect to x is this way, minus k. Thus, k is equal to minus d theta by dx. This term represents the decrease in phase with respect to distance along the direction of propagation of the wave. Now, d theta by dx. What is the meaning of this derivative of phase with respect to distance? There is the negative. Therefore, decrease in phase with respect to the distance along the direction of propagation of a wave. Already we have the definition of k wave vector. The decrease in phase with respect to distance or along the direction of the propagation of a wave is known as the wave vector. Therefore, that represented by k. K is equal to minus d theta by dx. Again, our equation of the wave y is equal to a sine omega t minus kx plus phi. In this equation, the angle omega t minus kx plus phi with sine function is the total phase of a particle at distance x from the source of a wave and at time t. It is denoted by theta. Therefore, theta is equal to omega t minus kx plus phi. The rate of change of theta with respect to distance x at time t. Therefore, theta is this. We are taking the derivative of this theta with respect to x. D theta by dx is equal to d by dx into bracket omega t minus kx plus phi. Omega t and phi are constant with respect to position x. Therefore, only the derivative of minus kx is minus k. Thus, k is equal to minus d theta upon dx. Is the decrease in phase with respect to distance along the direction of propagation of a wave. Thus, the wave equation for a wave, one-dimensional progressive harmonic wave propagating along positive x direction is y is equal to a sine omega t minus kx plus phi. Now, what is the wave equation for progressive harmonic wave propagating along minus x direction? So the wave equation for a wave propagating along the minus x direction is obtained by replacing the x by minus x in this equation. Therefore, this x, this minus becomes the plus. Therefore, the wave equation for progressive harmonic wave propagating along minus x direction is y is equal to a sine omega t plus kx plus phi. Here only the change is this. From the sign of x, we can judge about that the wave is propagating in which direction. If here negative sign, so the wave is propagating in positive x direction. Here this term is positive, therefore we can say that the wave is propagating along minus x direction. Clear this thing? Okay. Now after that, explain the magnitude and phase of a wave. Already we discussed and we defined the magnitude and phase of a wave. Again, what is the magnitude? What is the amplitude and phase of a wave? Just me. What is amplitude and phase of a wave? Now, magnitude of maximum displacement of a particle taking part in the propagation of a wave is known as amplitude of a wave. Again, the magnitude of maximum displacement of a particle taking the part in the propagation of a wave is known as amplitude of a wave. Already we know that as the disturbance enter in the medium. So, according to the distance, the particle of the medium oscillate about their mean position. What is the magnitude of maximum displacement? Maximum displacement of the particle taking the part in the propagation of a wave. That is known as the amplitude of a wave. Now, wave equation propagating in positive x direction. Y is equal to a sine kx minus omega t plus phi. Right? The maximum value of this term, sine kx minus omega t plus phi, is plus or minus 1. Therefore, we substitute therefore for maximum displacement, y maximum is equal to a plus or minus 1. Therefore, a plus or minus 1. But amplitude of a wave is always positive. Therefore, y maximum is equal to a. Again, from the equation of the wave, y is equal to a sine kx minus omega t plus phi. Now, the sine function has the maximum value is plus or minus 1. Therefore, for maximum displacement, we have to take the value of sine function is maximum. Therefore, y maximum is equal to a into bracket plus or minus 1. Therefore, y maximum is equal to plus or minus a. Now, the amplitude of a wave is always positive. Therefore, mod of y maximum is equal to a. Now, amplitude of wave is always positive. Therefore, y max is equal to a. And its SI unit is meter and dimensional formula is M0, L1, T0. Again, what is the definition of amplitude? Magnitude of maximum displacement. Magnitude of maximum displacement of a particle taking part in the propagation of a wave is known as the amplitude of a wave. Here the magnitude of maximum displacement of a particle taking the part in the propagation of a wave, that is known as amplitude of a wave. Now, what is the phase? Initial phase. Just we discussed that. Here, the angle with the sine function kx minus omega t plus phi is known as the phase of a wave at time t and at position x. Okay. The initial position of a particle at origin of a wave, that means that x is equal to 0 and at time t is equal to 0 is obtained by substituting the x is equal to 0 and t is equal to 0 in equation y is equal to a sine omega t minus kx plus phi. Right? As we substitute the x is equal to 0 and p is equal to 0 in this equation, we obtain y is equal to a sin phi. That represents the initial position or the initial phase of a wave. Now, in wave equation, y is equal to a sin omega t minus kx plus phi. Omega t minus kx plus phi is known as total phase of a wave at time t and at a distance x from its source. So, this term is the total phase of a wave, or the phase of a wave at time t and at position x from the source of a wave. It is also a total phase of a particle. It is also a total phase of a particle taking part in the propagation of a wave. Again, initial phase. The initial phase is obtained of a particle at origin of a wave and at time t is equal to 0 is obtained by taking t is equal to 0 and x is equal to 0 in y is equal to a sin omega t minus kx plus phi. So, in this part, we take the t is equal to 0, x is equal to 0. Therefore, initial phase is equal to y is equal to a sin phi. So, phi is our initial phase. Now, in equation this, omega t minus kx plus phi is the total phase of a wave at time t and distance x from its source. There is also the total phase of a particle performing the simple harmonic motion and taking the part of propagation of a wave. Clear this?